Ladies and gentlemen, welcome back to lesson 15 in group theory. This lesson talks about Lagrange's theorem and its important consequences. Lagrange's theorem is one of the most important and influential theorems in group theory. Not only does it prove our intuition, it confirms our intuition that when you take a normal subgroup of a group and you take the cosets of this subgroup, you end up with sets that have equal number of elements each. Not only does it confirm that suspicion, but also it formalizes the concepts about taking the quotient group. So here we have an example of Z8Z. So Z8Z is a cyclic group made up of 8 elements. And if we take the normal subgroup H, which is composed of 2 elements, 0 and 4, this H can be taken to be the cosets of H. So we can now take the cosets of H, 1 plus H, 2 plus H, and 3 plus H. We notice that each of the cosets of H contain 2 elements. So they contain the same number of elements. In other words, the 8 elements here are divided up equally amongst the cosets. That is essentially the essence of Lagrange's theorem. If you have a group of 8 elements and you take a normal subgroup of 2 elements, if you want to know the number of cosets it generates, just divide 8 by 2, you get 4 cosets. So this is what we're going to be proving. And afterwards, we're going to be seeing some very nice consequences of this theorem. One of which is that the order of any element in the group will divide the order of the entire group itself. So if the group had order 15, then we can only have elements of order 1, 3, 5, and 15. The next result says that groups of prime order, in other words, their order is a prime number, or their order is a product of 2 primes, are going to be classified in a certain way using Lagrange's theorem. The last result says that subgroups of index 2 are normal. Index is something that we're going to be defined just after proving Lagrange's theorem. Let's get to it. The statement of Lagrange's theorem goes as follows. Let G be a finite group and H a subgroup of G. Then the order of H divides the order of G. Moreover, the number of distinct left cosets or right cosets of H is equal to the order of G divided by the order of H, just exactly as we've mentioned in the example in the introduction. And this is equal to the order of the quotient group GH when GH is a group, of course. In other words, when H is a normal subgroup. So this result is not just restricted to when H is a normal subgroup. This is in general for any subgroup H, and when we take the number of distinct left or right cosets, we get the order of G divided by the order of H. Let's get to the proof. The proof of Lagrange's theorem is done by first realizing 2 important facts. The first fact, which has been proven, that the cosets of H partition the group G. In other words, G is exactly equal to the union of the cosets of H as little g goes through the group G. And moreover, if 2 cosets are distinct, then their intersection is completely empty. That is something we have already proven. G is finite. That is a very important fact because it has a finite number of elements that we can divide up. If it had an infinite number of elements, we cannot do that. So since G is finite and it's partitioned by the cosets, we can say that there exists a finite number of group elements, G1 through Gn, in G, such that G is equal to the disjoint union. So not only it is a union, but a union where all of the cosets GIH are disjoint from each other as I goes from 1 to n. So this is disjoint union. So because G is partitioned this way into these cosets, if we take the order of G, this will be exactly equal to the sum of the orders of each coset's GIH as I goes from 1 to n. The reason we can do that is because the union is disjoint. If it were not disjoint, then we would have elements in the intersection, and that could not give us the same sum as the order of G. But because they're disjoint, then the order of the entire group can be taken by adding the order of the individual cosets. So now we will make use of a proposition we've seen in lesson 14. We know that the cardinality of each of these GIH is exactly equal to the order of H, because there is a bijection between H and any coset of H. And this is true for all I between 1 and n. By the way, n represents the number of the distinct cosets of H. So because each of these cardinalities is equal to H, we can simply replace this by the cardinality of H. So the order of G is equal to the sum as I goes from 1 to n of the order of H. Now, whereas before this depended on the choice of I, now this is independent of the choice of I. So we can simply factor this outside the sum. So this is equal to the order of H times the sum of 1 as I goes from 1 to n. And this here is nothing but 1 plus 1 plus 1 n times, and that is equal to n. So this sum here is equal to n times the order of H. So we successfully proven that the order of G is a multiple of the order of H. So the order of H divides the order of G, and n is equal to the order of G divided by the order of H, where n is, again, the number of the cosets of H. And if H is a normal subgroup of G, then all that does is tell us that GH is a group, which is the quotient group of order n. Since this is the set of cosets and there are n cosets, so it has an order n. And that completes the proof of this very important theorem. Immediately after proving Lagrange's theorem, we'd like to define this n that we've seen in the proof, and this is exactly what we're doing here. Definition: the number of cosets in the set of cosets, GH, is called the index of H in G, noted by this notation, brackets, G colon H brackets. And if G is finite, so notice that this definition is for both infinite and finite. But if G is finite, we can use Lagrange's theorem to say that the index is equal to the order of G divided by the order of H. Let us now get into the consequences of Lagrange's theorem. Very useful results which have arose immediately after proving Lagrange's theorem. The first one being that the order of any element in the group will divide the order of the group itself. This is in the form Corollary 1. Let G be a finite group and little g an element in G. Then we have that the order of G divides the order of big G. In particular, if we take G to the power of the order of big G, we get the identity element. So proving this will be, of course, harder than proving this because this is an immediate fact after this. by the definition of what the order of an element is. If you've forgotten what the order of an element is, I highly recommend you go back in lesson 3 in the playlist and check it out. To prove this corollary, we will use, of course, Lagrange's theorem. So we will apply Lagrange's theorem, but for Lagrange's theorem, we need a finite group and a subgroup of G. We have already a finite group G. All what we need is to choose what our H will look like. Well, what do we have? We have the element G here. And what can we get from G as a subgroup? We can get the cyclic group that is generated by G. So our choice of H will be the cyclic group generated by G. What do we know about cyclic groups that we've seen before? We know that the order of H, the cyclic group, is equal to the order of the generating element G. So we can say the order of G is equal to the order of the cyclic group generated by G, and that is by virtue of it being a cyclic group. We have already proven that result in the lesson Cyclic Groups. And now we can use Lagrange's theorem to say that the order of the subgroup divides the order of the group, therefore proving this result here. Now, the proof of the second part is going to be very, very immediate because this is the definition of what an order is. If the order of the element divides a number and you take that element to the power of that number, you will get the identity. It immediately follows that G to the power of the order of G is equal to the identity, thus proving corollary 1. Now, if that wasn't a strong enough result for you, how about the classification of all groups of prime order? This is corollary 2. If G is a group with a prime order, then G is a cyclic group, and G is isomorphic to ZPZ. So we have just classified all of the groups with prime order. Let us get into the proof of corollary 2. Let G be a group such that the order of G is prime. We want to prove that G is a cyclic group. We know that since the order of G is a prime, and the smallest prime number is 2, then we have to have that the order of G is strictly bigger than 1. If the order of G is strictly bigger than 1, there has to be at least 2 elements, the identity element and some other element which is not the identity. So let G in G be that element that is not the identity. Again, this is possible because the order of G, being a prime, is bigger than 1. This means that since it's not the identity, the order of G is not equal to 1, since the identity is the only element with order 1. And by corollary 1 of Lagrange, we have that the order of the element divides the order of the group. But what is the order of the group? We have supposed it to be P, a prime number. And now we need to look at the positive divisors of P. The positive divisors of P are 1 and P. Because P is a prime number, there are no other positive divisors. Since the order of G is not equal to 1, it has to equal P. That is the only other choice. But P is the order of the group. So essentially we're saying the order of the element is equal to the order of the entire group. But that is a property for cyclic groups. So G is nothing but the cyclic group generated by small g. And we are done because the isomorphism here is a result we've already proven for all cyclic groups of a certain order. If a cyclic group is of order n, then it is isomorphic to Z and Z. So here the cyclic group is order P, so it is isomorphic to ZPZ. So essentially, we have completed the proof of corollary 2. Now that we got one important classification out of the way, let us do another. Let G be a group such that the order of G is the product of two primes, P and Q. Then, G is abelian, or the center of G contains only the identity. Let's get down to the proof. To start off, we'd like to get the trivial cases out of the way. If the center contains the identity or G is abelian, then we are done. So a priori, if this information is given to us, then we are done. There is nothing to prove. Now, if ZG is not equal to the set containing 1, we would like to prove that G is abelian, since the result says either this or that. So if it's not this, then it must be that. Okay, since the center of G is a subgroup of G, we can use Lagrange's theorem to say that the order of the center divides the order of the group. But the order of the group is equal to P times Q. So if we had, for example, the number 3 times 5, 15, what are the possible divisors of 15? The possible divisors are 1, 3, 5, or 15, which is 3 times 5. And that is exactly the case here. For P and Q, any two primes, we have that the possibilities for the order of the center of G to be 1, P, Q, PQ. Okay, now I'll show you that it cannot be 1. The order of ZG cannot be equal to 1. And why is that? Because ZG is assumed to be non-trivial. We have that the order of ZG is not equal to 1. Okay, let us deal with the possibility that the order of ZG is equal to PQ. If the order of ZG is equal to PQ, which is the order of G, then essentially saying that ZG is equal to G because it contains as many elements as the entire group G. And this is specifically a property of abelian groups. It is where the center is equal to the entire group. So this leads us to prove that G is abelian, which is what we wanted. Now, this is done for this case, but what if ZG has an order P or order Q? What happens then? We need to investigate that possibility. If the order of ZG is equal to P or Q, doesn't matter which prime you take, without loss of generality, we can take it to be either one. Then, by Lagrange, we have that if we take ZG to be our subgroup, we can take the quotient group GZG, GZG, and the order of this is going to be equal to PQ, which is the order of G, divided by the order of ZG. That's going to be equal to PQ divided by, let's say the order of ZG was P, all right? So it's going to be divided by P, and this is going to be equal to Q. But because Q is a prime, and we've said that any group with prime order has to be cyclic by Corollary 2, we have that GZG is a cyclic group. Now, we need to go from this fact to the fact that G is an abelian group. And how do we do that? So, because GZG is a cyclic group, it can be generated by a single element. What do the elements of GZG look like? Well, they look like cosets. So, it is generated by a single coset. So, for any element, we can say that GZG is a group that is generated by a single coset, which is x times ZG for some x in G. This is a coset of ZG. Okay? And now, for any element G in G, if we take any coset of ZG, it has to be a power of this generating element. because as we said, this is a cyclic group, so all of the elements in this group has to be generated by this element here. So any coset GZG has to be a power of the generating coset XZG to the power of m for some integer m, which is equal to x to the m zg by definition of coset multiplication. And this is equivalent to saying, because here we have gzg, here we have x to the mzg. If we take x to the minus m on both sides of the equation, we get x to the minus mg is an element in zg. And if we take now x to the m, we get g is an element in x to the m zg. So essentially saying that g is equal to x to the m times some element in the center, z, for some z in the center. Okay, so every element in the group G can be represented as this product here, x to the m times some element in the center of G. Now, let A and B be two elements in the group G. We have, by this representation of the elements, that A is equal to x to the m times ZA, and B is equal to x to the n times ZB for some ZA, ZB in the center of G, and for some m and n, which are integers. So we can represent A and B as such. Now we need to prove that AB is equal to BA for any AB in G, thus proving that G is abelian. So let us just write it down and calculate it. A times B is equal to x to the m ZA times x to the n ZB. And now we will make use of the fact that ZA and ZB are elements in the center of G. Remember, the center of G contains elements which are commutative with all of the elements of the group. So what we want to do here is we're going to commute these two here, thus getting us the powers of x on one side and the elements of the center on the other side. Here we get x to the m, x to the n, ZA, ZB, and this is equal to x to the m plus n, ZB, ZA. We can even commute them with each other. And this is equal to x to the n plus m, ZB, ZA. This is equal to x to the n, x to the m, ZB, ZA, which is equal to, now we can commute them back after we have done our switching, x to the n, ZB, x to the m, ZA. And this, by definition, is equal to B times A. Thus, we have succeeded in proving that for any elements A and B in the group, A times B is equal to B times A, thus proving that G is abelian. Completing the proof of this very nice corollary, which classifies all groups of order a product of two primes PQ. The last result in this lesson is a very, very nice way to immediately say that a subgroup is normal. This proposition says that if G is a group and H a subgroup of G, then if the index of H by G is 2, then H is a normal subgroup of G. So just by calculating the index and having it equal to 2, we immediately deduce that H is a normal subgroup of G. To prove this, we need to realize that since the index of H is equal to 2, then H cannot be equal to G. Because if H is equal to G, then what can we say about the set of cosets GG? That would contain a single element. So the cardinality would be equal to 1, but this is just equal to the index of GH, but we've said that it's equal to 2, not 1. So that's a contradiction. So we have to have that H is not equal to G. In other words, if G is the group here and H is here, we have to have an element that is in G but not in H. So let G be in G such that G is not in H. If G is not in H, then the coset GH cannot be equal to the coset H. Now this means that we have found two distinct left cosets of H, which is H and GH. And of course, the index is always going to be equal to 2, and that is the cardinality of the set of cosets. So because the cardinality is 2, and we've just listed 2 elements, we have completely listed all of the elements in GH. So we conclude that the set of cosets GH is the entire set made up of H and GH. There are no other cosets. The same could be said about right cosets, where we conclude that GH is the set made up of 2 cosets, which is H and the right coset HG. So we've concluded that GH is equal to this and GH is equal to that. So that means by transitivity, H, GH is equal to H, HG. And since H and H are accounted for, this leaves us no choice but to say that GH is equal to HG. But this was assuming that G is any element in G. So this is for any G in G. But this here is the exact definition of what a normal subgroup is. It's where the left and right cosets are equal, no matter the choice of G. So this means that H has to be a normal subgroup of G, concluding the proof of this very nice result here. And with this, we have finished Lagrange's theorem. If you've enjoyed this very nice result, drop a like, subscribe, and share with anyone who would be interested in this very natural, intuitive, satisfying branch in mathematics. I'll see you all in the next time. Have a nice day, and bye.